When we started our discussion on transmission line modeling, I had mentioned that there are three parameters we need to concern ourselves with: resistance, inductance, and capacitance. Last few videos we've already talked about resistance, and we're going to start our series of videos on inductance today. But before we get into all the different configurations of our transmission lines, for a single phase line, for a three-phase line, concepts such as self-inductance, mutual inductance, single phase, three-phase lines. We're going to discuss all of these in the videos that are to come. But today I just wanted to do a quick recap of the physics of electricity that is related to inductance. So let's begin by defining inductance. What is inductance? Inductance can be defined as the property of a conductor such that any change in current through this conductor induces an EMF, an electromotive force. As simple as that. The key thing to remember is it's a property. So it's a physical property. It wasn't something that was invented. It wasn't something that was derived. It was something that scientists observed. So once again, inductance is the property of a conductor where the change in current induces an EMF. Let's look at some of the laws that help us better understand this concept. The very first one there is Oersted law, where it was observed that steady electric current produces a magnetic field. So steady electric current produces a magnetic field. That was one of the very first observations that we made related to electromagnetism. Then came Mr. Faraday, and he gave us the Faraday's law, which said that a varying magnetic field produces an induced EMF. So it induces an electromotive force. And then came Lenz's law, which completed our understanding of this phenomena. And what Lenz's law said is that the direction of induced current is such that it opposes the change that produced it. So these are the three laws, and let's look at them visually to help you better understand what they are. Now again, as power system engineers, we should already be familiar with the physics of electricity. So I'm going to be a little quick when I go through these concepts, but because this is just a quick recap of what we're going to be seeing in the videos to come as we discuss inductance of the conductor. So again, steady current produces a magnetic field. So let's go back and look at our cylindrical conductor there. Let's say there's a current I passing through it. This steady current will produce a magnetic field. And if we remember the right-hand rule, what it told us was the direction of this magnetic field. So if we take our right hand and if we point the thumb in the direction of the current, so if we point our thumb in the direction of the current, our fingers will wrap around in the direction of the magnetic field. So the magnetic field would be such, and the direction would be this way. So that's Oersted's law. That's what we observed. And then came Faraday. He said a varying magnetic field would induce an EMF. So how would we have a varying magnetic field? Well, we'll have a varying magnetic field if we have a varying current. So if we have an AC current, that's just symbolizing an AC current with the sine wave. So we have an AC current then we have a varying magnetic field, and that's going to induce an EMF. It induces an EMF in this conductor and in any nearby conductors. So if we have another conductor that is nearby, we're going to have an inductance, an EMF induced there as well. So any EMF that's induced in this conductor itself is called self-inductance, and any EMF that's induced here is as a result of mutual inductance. So once again, these are key concepts you need to understand. So any current passing through this conductor, it induces an EMF in this conductor itself, within this conductor itself, and that's self-inductance. And it also induces an EMF in any other nearby conductors, which is mutual inductance. So when you're calculating inductance in a transmission line, you have to consider two things. You have to consider the inductance that is being caused by the current passing through that conductor, which is a self-inductance, and you have to consider the inductance that is due to any other nearby conductors, which is mutual inductance. And we'll get into the details of this in the videos that are to come. So don't worry about that, but just wanted you to be familiar with these concepts. So these are the laws. Now let's look a little bit deeper. Let's go back a step further and define what is magnetic field itself. So magnetic field is basically the magnetic effect due to electric current. So again, it's the magnetic effect due to an electric current. So this is a magnetic field. This is the magnetic effect, which is again an effect of nature. It's an observation of the physical nature. And so any current, electric current, causes a magnetic effect, and that magnetic effect is the magnetic field that is created. We formulate it as H represents the magnetic field is equal to I over 2 pi r, where r is the distance from the conductor, and the units are, as you can see, amp over meter. Amp for the current and meter for the distance. What we can see is the magnetic field is inversely proportional to the distance from the conductor. So as you move further away from the conductor, the magnetic field is going to get weaker and weaker. Now this can be derived, this formula right here can be derived from Ampere's law, but I'm not going to get into that today at least. And there are a lot of videos on Ampere's law if you search for them, and they give a very good explanation of what it is. So I'm just going to leave it at that. I just wanted to highlight this formula right here because it is something we will be using as we move forward. A concept similar to magnetic field is magnetic field density, which is formulated as B is equal to mu times H. So it is very similar to it is equal to the magnetic field, except there is a constant here, mu, which is the permeability. My spellings are horribly weak, so let me just make sure I'm spelling this correctly. Permeability, yes. So it is the permeability of the medium in which we are measuring our magnetic field. So permeability mu is defined as mu r times mu naught, where mu r is the relative permeability and mu naught is the permeability of free space and mu naught is equal to 4 pi times 10 to the power minus 7 Henry per meter. What is Henry? I forgot to mention up here. Inductance, the unit of inductance is Henry, which is, so we use the alphabet H to represent the unit. So it's a little bit confusing, but keep in mind this H is different from this H. This H is the unit for inductance representing Henry, and this H is the magnetic field. And we have B as the magnetic field density. The unit for magnetic field density is Tesla, and we use the letter T for that. So let me highlight that for you. Let me highlight this for you. So permeability of free space. So for example, if you're measuring it, permeability of free space is basically permeability of vacuum. If we are measuring the magnetic field density in air, for example, then we would multiply it with the relative permeability of air, which is generally assumed to be 1. So for most of our calculations, when we are using this formula to calculate the magnetic field density and such other quantities for transmission lines, we would basically be using mu naught for mu. I will mention that again when we get into those situations, but I just want to reiterate that here, so you remember that and you note that. So we've defined magnetic field, we've defined magnetic field density. Next comes magnetic flux. So what is magnetic flux? It's defined by phi or phi, as you want to pronounce that. That is equal to B, which is the magnetic field density, times the area times cos theta. That is the mathematical formulation. What is the definition? The definition is simply that it is the measure of the magnetic field density through a closed surface. So this is the area of that surface. I am going to make this clearer for you, don't worry. So let us draw ourselves some magnetic field lines. So these are magnetic field lines. So we mentioned that the magnetic flux is nothing but the measure of magnetic field density through a closed surface. So I have drawn some magnetic field lines here. So those are our magnetic field lines. Let me draw a closed surface here like a circle. So let's take a circle and draw it around these three lines here. So the magnetic flux is all the magnetic field lines, so the measure of the magnetic field density passing through here. So for example, there are three lines through the surface, so we can say magnetic flux of 3 here. This is just a very layman way of explaining it, but I hope to just get the concept across to you. The unit, by the way, for magnetic flux, so let me write that. The unit is Weber, which we use WB to define that. Now you're wondering where this formulation comes from. So let's look at magnetic flux. If it's all the amount of field lines passing through a closed surface, right? So what will affect it? One, of course, the magnetic field density here. So there are 3 lines here. What if I was to increase the number of lines? So that is one way I can increase my flux. Now increase the amount of field lines going through there, so I have more flux. What is another way? I can increase the area of my surface. So instead of these 3 lines passing through, now I have 1, 2, 3, 4, 5 lines passing through. So I can increase my area. That is another way. So the first method was you can increase the amount of field density. So you can increase the field density, or you can increase the area and you can increase the flux. What's another way? Well, another way is that we can change the angle. So here you see this is making, if you look at the normal of this surface, so normal of this surface is a vector that is perpendicular to it. So the normal of this surface is parallel to the magnetic field lines. What if I change the angle of my surface? And now my normal, this is my normal vector to the surface. This is making some angle here, right? Which is greater than 0. And I can make another, I can go to another extreme and have a surface which is parallel to the field lines, and then my normal is making an angle of 90 degrees with the surface as well as with the field lines, and then there are no the magnetic flux through this surface is 0 because it's parallel to the magnetic field lines. So that is where this angle comes into play. So there are 3 things that the magnetic flux depends on. It's the magnetic field density. I can change the magnetic field density and change the flux. I can make the area larger or smaller, or I can change the angle of the area and my magnetic flux would change. The next concept that we want to quickly touch upon is the magnetic flux linkages. Magnetic flux linkages are mathematically given by lambda, which is equal to n times phi, where n represents the number of turns, so number of turns of this surface area. So once again, let me draw some more field lines. So you have magnetic field lines here, and you have a surface area, so you can have it once. What if you have it twice? You have it thrice. So there are, this n here is equal to 3. So my flux linkages would be 3 times the flux that is there. So it would be n times b a cos theta. So that is my flux linkages. Why did we have to get to all of this? Well, this is why, because the inductance of a transmission line, so an inductance of a transmission line is mathematically represented by L is equal to lambda by I, and that is the formula I wanted to represent. It's the unit is Henry. So it is basically the amount of flux linkages that are attached to the current through the conductor. And so as we move forward, what we will see is, what we would basically be interested in is for different configurations of a transmission line. I know I've been repeating that word, different configurations. What do I mean? So let's look at a transmission line. Okay, let me draw that properly so you understand it. If you've observed transmission lines, so you could have a transmission line where the conductor is here, here, and here. That's a transmission line pole, and that's one configuration, for example. Then you could have transmission lines that are like this, and this. Sometimes there are 2 sets of transmission lines on the same transmission, on a transmission tower. So these are different configurations of a transmission line. These configurations will affect the flux linkages, and that's what we would aim to calculate from these flux linkages. That is what will give us the inductance of this transmission line. So that's what I wanted to get into. That's why I wanted to just quickly go through all these formulas. So very quickly, we defined inductance as a property of the conductor where the change in current induces an EMF. We saw three laws: that a steady current uh, leads to a magnetic field, a varying magnetic field induces an EMF, and the direction of the induced current, due to this induced EMF, we have an induced current. The direction of this is such that it opposes the change that produced it. Let me quickly see if I mentioned that up here. So if we go back up here, I think I missed that. So I mentioned self-inductance and mutual inductance. So I did discuss Faraday's law where a varying magnetic field induces an EMF, but this induced EMF leads to a current. This current is such that it opposes the current that is causing this. This is the change. The changing current is causing the changing magnetic field, which is causing this current. So the direction of this induced current I prime, for example, let's say, would be opposing this current. So similar to resistance, where resistance was making the flow of this current difficult, the inductance does the same by inducing a current which is opposing the change or the current that is causing this. I hope all of that is clear. So we went into the laws, we discussed the magnetic field, we defined it, or we mathematically stated that H is equal to I over 2 pi r. We went into magnetic field density, where we defined it as we defined the concept of permeability, which is a constant for a medium. We defined what is magnetic flux, and from there we got flux linkages, and from flux linkages we defined what is the inductance of a transmission line. So that was a very quick physics lessons, but as I mentioned, as power system engineers, we really don't need to get into the nitty-gritty physics of things. What we really, our aim is to be able to mathematically define transmission line parameters like resistance, which we saw in the previous videos, and like inductance, which we'll see in the next few videos. We'll mathematically relate the inductance of a transmission line to the physical properties of the transmission line, so we can use them in algorithms, in software programs in the future. So I'm really hoping these videos are bringing some value to you. I'd love to hear from you. I'd also encourage you to please subscribe to our channel. There are tons of other free videos I've planned and that we'll be uploading in the next few days and weeks. Also sign up for our newsletter at movingelectrons.com. Once again, thanks for all the feedback that I've received so far. Take care till next time and have fun.